think we are ready to start. Almost Miami time, so I have to take out my cheat sheet. So thank you for attending the seminar on strategic research initiatives. And today we are really grateful to our Provost, Dr. Duerk, to take time out of his busy schedule to give this seminar. Hopefully you all know that this is our Provost. One thing you may not know is that Dr. Duerk is also faculty in our Department of Biomedical Engineering. So he's been at the university since July 2017, and before that he was at Case Western University for about 30 years, I think, where, if I go in reverse chronological order, he was Dean of Engineering, Chair of the Department of Biomedical Engineering, Vice Chair of Radiology, and faculty for a number of years. He was also Director of the Case Center for Imaging, and before that he got his PhD in Biomedical Engineering from Case Western University, his Master's in Electrical Engineering from Ohio State, and his Bachelor's in Electrical Engineering from Purdue. Dr. Duerk is an expert on MRI imaging. There's more than 200 papers, I think, about 40 patents also. And also he has a number of leadership positions in all of the major societies that are relevant to us: IEEE, the International Society for MRI, BMES, IABE, and since last year he's been a member of the National Academy of Inventors. Let's welcome Dr. Duerk, and I guess he's going to show you, or maybe the formula disappeared, but that
no.
Thank you.
Yeah, thanks everybody. So the first thing I'd like to say is just how great it is to talk about MRI for the first time in a long time. I spent, as Fabrice said, I spent 30-some years in the field, and this is my first chance since coming to Miami to really have a chance to talk a little bit about science. But I thought it was also a nice metaphor, looking back over 30 years, for what I learned being in an interdisciplinary field and also at the start of a field, because as you'll see in a second, when I got into MRI in the early 80s, it was really in its very earliest stages. So one of the things I think about when I think about team science is, you know, what it really is a group of investigators who are working together to solve a problem. And my corollary to that is team science is best practice when the problems that you're trying to tackle are really big and hairy. You know, if it's how to tie your shoe, you don't need a team of scientists to do that. But if you want to transform MRI from a tool that's used in diagnostic imaging to one that's actually used for real-time image-guided cancer therapies or cardiovascular therapies, then that's a pretty big paradigm shift, and that's really what I'm going to talk about here. So one of the things that's, I think, important to put in context about this is team science is really popular now. For the faculty who are here, all of you know that when we look at our NSF grant applications, our NIH grant applications, the thing we're being asked for is relevance. Why is this problem big and hairy and meaty and important? And what are all the disciplines you're going to bring together? So I want to give you a little bit of a context. So John Bixby is the Vice Provost for Research, and he and I are about the same age. And when we both started our scientific career, on average, in most scientific publications, you'd have about 2 to 3 authors on a paper. And yet, if you look at it today, it's somewhere in the neighborhood of 7 to 8 on average. So team science is really a fundamental sort of way of how our careers are going to be practiced. Now, the downside of team science is it's hard, okay? You have to form a common language. There's a lot of things you have to do to recognize that you're going to miscommunicate more than you would if you're just dealing with members of your lab. There's also going to be periods of time where the effort is uneven, where you're working harder than your colleagues. But if you take the perspective that there's going to be another time where their load is going to increase and it's going to balance out in the end, things are going to work out fine. But if you recognize these things up front, there's value to sort of the team sort of coming together. And there's other things like a little bit slower productivity to start with, and sort of technological fails, I think, happen more often because you may be the technical expert in your area and somebody else may be the technical expert in their area, but the problem you're going to tackle tackle is going to be where those things come together. And so things aren't going to work out like you thought. But on the positive side, you can really tackle bigger problems, and you can have these increased sort of dynamic relationships and increased creativity, and as I said before, just sort of generally more funding. So what I want to talk about today is give you a little bit of understanding about MRI, because I think you'll have some appreciation for why I say it's an interdisciplinary team that sort of we work together. So I have to give you a little bit of understanding of how MRI actually works, and then we'll sort of get into sort of where the team application comes in. And I'm not going to go into like the hardcore physics of MR, okay? But I'll give you a sort of an introductory level of that, but more importantly, how it all comes together. So first, we'll talk a little bit about some historical context of biomedical imaging, which I contend is the first of the interdisciplinary team scientists. Talk a little bit about quantum physics and some engineering. Talk about some tidbits in team science intermingled through with my two friends, John Bixby and John Lewin. I'll point out John Lewin was a colleague I worked with for 12 years together at Case Western Reserve. He left and went on to be the chairman of radiology at Johns Hopkins, and he's now the head of Emory Health, the entire health system at Emory. So we both seem to have done okay with this whole team science thing. So a fundamental principle as well is share the glory. It's amazing what you can get done when you look at it from the perspective of there's going to be plenty of glory to share, so don't worry about who gets it, because you're going to be looking at sort of these big problems. So my contention is biomedical imaging is about 100 and some years old at this point. In 1895, Röntgen discovered X-rays. That's his wife's hand. That's her wedding ring on her finger. And one thing that you should know about X-ray imaging and Röntgen is there are no X-rays of Röntgen himself. He took them of his wife, but not of himself, because he didn't know and he was scared. And now we know for good reasons. Again, however, 4 months later, so think about this, 1895 he discovers X-rays. 4 months later, 4,000 miles away at Kenyon College in Ohio, this is an X-ray image of a judge taken with a nail in his hand. And this letter is describing the relationship between the physician and a physics professor at Kenyon College, where they hooked up basically a paddle wheel and a waterfall to drive the generator that ultimately drove the X-ray tube to create the X-rays. So it was a collaboration between a physicist and a physician that gave rise to those images. And that's my contention of the first interdisciplinary application of imaging. And if you look back sort of from 1896 to 1950s, the X-ray really didn't change at all. Maybe the planes, maybe the anatomy, but for the most part, things didn't change. And it wasn't until the advent of cross-sectional imaging, the CT, that we really started to getting into sort of really diagnostic cross-sectional imaging, because this is a projection modality, X-ray, where I'm looking through the whole body. And in this particular CT scan, what we're doing is taking specific rows out of the image to create this sagittal plane. Now in CT, look at the level of detail we can get in the actual images. Same plane, but 20 years different. We can do things like combine modalities. In this particular case, a CT scan, a PET scan, all integrated into one device. Put that information together and get both anatomic information, but also metabolic information. So I can get cancer because of the metabolic information and anatomic localization because of the CT. Now, as I said before, I got involved in MRI about 1983. This was the image quality in 1981. This was image quality in 1984. I got in the field right around here. In 1983 in Cleveland, Ohio, where I was pursuing my PhD at Case Western Reserve, there were more MR scanners in Cleveland, which was I think 6, than all of Europe at the time. So it was a hot spot to be. And if you look at the change in the image quality in sort of 30 years or so, not only has the quality of the image changed, but so has the acquisition time. The acquisition time is a fraction of what it was before because of all the technological advances. But not only have the images changed, so have the imagers. This was me in 1981, me today, but everything about the field changes. And so in 1983, when I was working on my Master's of Science in Electrical Engineering, was the first time I heard about this new field called NMR imaging. And what I was told was there were going to be huge electromagnets, there were going to be radio frequency transmitters and receivers, there was a new technology out called digital signal processing because microprocessors were just sort of emerging at that point in time. There was quantum mechanics that I knew nothing about. But when I heard about all the electrical engineering, I said, that's the field I want to be in. And I figured, I said, I will learn the physics, I will learn the clinical applications, but I sort of get and I'm excited about the electrical engineering, and I just figure I'll learn the rest. Whoops. So as I said, I knew there were going to be big electromagnets, big bunch of loop of wires, put some current through it, radio frequencies, digital electronics, and this other thing called Fourier transform that hopefully most of you who are engineering students know something about. And these other things, the quantum mechanics, radiology, and also the disease and stuff, I said, I'll learn that down the road. So I want to start with some quantum physics, okay? And the first thing you need to know about the nucleus is protons have positive charge. They also have a quantum property called spin. So if you take a spin or a charge and you spin it, what do you get? You get a current. And if you get a current, you're going to get a magnetic field. And if you put a magnetic field or a magnetic moment, and you put a magnetic moment in a magnetic field, that magnetic moment in the magnetic field is going to precess around the magnetic field in exactly the same way a gyroscope precesses about a gravitational field. Because this gyroscope is going to have angular momentum, and it's going to be acted on by forces. The forces, in this case, in just a second, is going to be gravity. So if this thing works, Anna, we'll see. Okay, so I have to get this thing going. So it's going to precess about the gravitational field, right? You see it precessing? The frequency of that precession is based on the moment of inertia and the strength of the gravitational field. Okay? This motion is exactly the same thing that happens with the spin in the magnetic field. So spins or protons are going to precess about any magnetic field they see. That's sort of the first lesson you have to learn. Spins are going to precess about any field they see, and there's going to be a specific frequency at which they precess as well. That's dependent on the strength of the magnetic field and the size of the magnetic moment. And for protons, the magnetic moment's fixed. It's a quantum property. Okay, so why is it that right now none of you have any magnetic moment to speak of? We know you have protons in your body. Your body has gazillions of protons, but there's no magnetic moment. And the reason is you're in such a weak magnetic field. You're only in a magnetic field of about half a Gauss. So the thermal competition between your protons trying to line up with respect to the magnetic field of the Earth and the thermal energy of our body prevents there from being any net magnetization. So I need a big magnet. And in fact, the magnets we use for MRI are about 30,000 times the strength of the magnetic field. And even then, only a small fraction of the protons actually line up with the magnetic field. I think it's about 15 per million per Tesla. So I have to create this really large magnetic field. And I'm going to do that by creating a big electromagnet. And that magnet has to be big enough for you to get inside of. Now, how many of you have had an MR scan? Okay, virtually everyone, right? Okay. And I guarantee almost any of you that have had a scan have somehow used or benefited from some of the technology that I contributed to. And what I'm going to tell you in a few minutes is the one question you all want to know is, why is it so loud? Okay, and we're going to get to that in a little bit. Okay, so the spins are going to align. I know that they're going to be precessing at about 64 megahertz if my magnetic field is about 1.5 Tesla, which means if I want to do anything with that magnetization, I have to apply an RF pulse, a radio frequency pulse of energy at about 64 million cycles a second. So the first lesson I learned when I got into this field was respect your colleagues as your peers. I knew nothing about quantum physics. I knew nothing about spin. I knew nothing about NMR spectrometry. I didn't know any of that stuff, but they did, and they were great teachers for me. Learning something new is really fun. Okay, this was probably the most challenged I ever was in my life to try and put all of this stuff together. But those new colleagues I had really provided me with a new armamentarium of skills and perspectives that I knew I was going to carry with me for the rest of my life. And as frustrating as it was, and as challenging as it was, I just had to keep telling myself to be persistent and be patient. So the other thing I'll share with you just right off the bat is different tissues have different biochemical and mechanical properties. And it's those properties that are going to manifest themselves in the images. We already know that we're going to put people inside of big magnets. We know, because I've already talked about, that we're going to give pulses of radio frequency energy. And the timing between those radio frequency pulses of energy are what I'm going to use to generate contrast between the tissue. This is basically the same slice of anatomy, simply where I have the information to create the image collected at 2 different times, 2 different ways to collect the information. And you can see the gray matter is gray, the white matter is white. In this particular acquisition, in this particular case, the gray matter is sort of a whitish, the white matter is sort of a grayish, and the cerebrospinal fluid is white. Same tissue, same person, just collected the data 2 different ways. And so you can appreciate, sometimes I may want to get anatomic information, and sometimes I may want to get information where the differences between normal and pathologic tissue are really different. Okay, so my challenge is the magnetization from each of you when you got in the magnet was lined up in the same direction as that big magnetic field that I used to create my, the big electromagnet. So this is about 30,000 times the strength of the magnetic field of the Earth. This is about 300,000 or 1,000,000 times weaker than that. So this is a really small bit of magnetization pointed along the main magnetic field that I created. This is the classic needle in a haystack problem. How do I detect this when it's billions of times smaller than this? So how would you do it? Well, the first thing would be make it so it's not pointed in the same direction. Get it to point somewhere else. Because I know that as soon as it's pointing somewhere else, it's going to precess or spin about that magnetic field. It's not going to be static along the static magnetic field, but if I can change its orientation, so I have to give an RF pulse. And when I do that, this is my RF pulse, my magnetization tips over. Now they're not aligned anymore, and I don't have that needle in a haystack problem anymore. Oops. Okay? These are the equations of motion that are described by those figures there. Pretty simple differential equation. Okay? With a couple things. One is it tells me something about the tissue properties of T1 and T2. These are just parameters of the tissues I'm trying to image. But other than that, pretty much everything else is under my control. I can turn on and off the magnetic fields, the RF pulses. I control everything else besides this and this, which is pretty cool because these are equations that any of us could write a MATLAB program to simulate. One of the big advances of MRI, or big realizations I think that drove MRI forward, is the fact that so much of it is simulatable. So one of my lessons learned was old materials learned well, open new doors. Don't throw away old tools. I remember differential equations from my 2nd year of college when I was a grad student, and that completely opened up the door for MR to me with very little review. So once I take that magnetization and I knock it over, it's going to spin around. Okay? So what can you do with a magnetization that's spinning around? Imagine I had a bar magnet that was spinning around. Could I create a detector for that? A simple loop of wire, right? So what I'm going to do is create a coil of wire to detect that magnetization tipping around. It's going to induce a voltage in a coil, and I'm going to amplify that signal, and then I'm going to digitize it. So now I've taken my magnetization, I've tipped it over, I've induced a voltage. I'm pretty close to imaging at this point. All right. But to do imaging, I need to be able to differentiate head to foot, left to right, front to back, because I need to know where that signal came from. Now I know that the spins are only going to precess about any magnetization that it sees, and it has to be at the right frequency. So what I'm going to do is turn on a gradient that makes the magnetic field vary from head to foot. Now every position is at a different frequency. Just like every note on a piano is at a different key, and if I want to detect this location, I have to apply this frequency of radio frequency energy. If I want to select this location, it's a different frequency altogether. I have a one-to-one relationship between frequency and position, head to foot. I apply a range of frequencies. That selects a range of positions, and I get a slice of tissue. Okay? And the pulse, or the rate that I apply the radio frequency pulses and a bunch of other things control how my magnetization evolves. And if I think about the left-right problem, again, I'm going to turn on some gradients, left to right. All of this stuff has to get packed inside of a tube that you're going to lay in. So I'm going to have thousands of loops of wire to create that main magnetic field. I'm going to have some other coils that make the gradient field from head to foot, from left to right, from front to back. All of those are under my control. And I'm going to have a loop of wire, a detector, a receiver coil, in which to get the signal. All of that is what goes inside the MR imager. Okay? And we still haven't gotten to why it's so noisy, though. So I'm going to apply a gradient, left to right, head to foot, etc. I'm going to detect a signal that's now the Fourier transform of the object. And if you look at the equation of actually what I detect, this is my body, this is you. These are the gradients I turn on. This is my receiver coil. This is now starting to look an awful like a Fourier transform. This is my object. So I'm imaging a person. I'm applying a function along the x-axis, another function on the y-axis. This is just a Fourier series in some ways. So the signal I'm collecting is basically the two-dimensional Fourier transform of the person, of that slice of tissue that I excited. Yeah?
And for Z, you just do different size.
Yeah. Yeah, I turn on a gradient, and then I apply a specific range of frequencies that detect or knocks over a specific range of tissues. And so all of that banging, all of that stuff that you hear is simply the gradients turning on to select a row and then collect data across that row, and then bang again, move across the row. And in a raster-like fashion, all of that banging is just moving to a new row and across the row to get all the information I need. Such that when I do the two-dimensional Fourier transform, I get the image. So all of that banging, all of that stuff, think of all those minutes you laid inside the scanner and heard all of that stuff. It was selecting slices, moving left to right, moving across the rasters, moving down from row to row at each different slice location. Now I want to give you a sense of this data, okay? Because I have, if it's a two-dimensional Fourier transform, some of the information is going to be low frequency and some of it's going to be high frequency. So let's go to this very low frequency part of the data. In fact, let's just look at a 6x6 area, 36 points, and reconstruct the image. Can anyone tell what that is? You can see contrast, right? You can see blobs of contrast. You can sort of see an average level, a DC level in the image. But there's no high frequency information. There's no edges. So let's add a little bit more data. 256 points. Any guesses? Okay. But can you tell what Mickey's standing around? Where's the resolution? We only have 900 points here. You can tell it's Mickey. This looks more like a nuclear medicine image than an MR image. I'm poking fun at my pet and nuclear medicine friends. Okay? So I need all of this information in order to get the detail. And when a radiologist is setting up the scans, they're making that choice between how much resolution they need, how much contrast they need. And they're going to spend that much time in order to get this much information to do that. Now let's go the other way. Let's just look at the outer edges, where the high frequency stuff is now. And now you can see some edges, but what you don't have is any contrast. So I'll buy, whoever can guess this first, a Starbucks gift card on what this is.
Oh, it's
Do you have it?
Yeah, it's the guys.
Okay, well, what's that called?
It's a picture of the farmers.
It's a
Yeah, I know.
American Gothic. But look at this. You have 3/4 of the data, and yet you still have no contrast. You only have edges. You have all but 6 lines of data and still no contrast. American Gothic. So I'll give it to both of you guys. Stop by my office. It'll be a cheap gift card since you have to split it. Okay. So the bottom line is I have to strike a balance between how much information I collect. And in MR, information is typically considered to be time, because I have to raster across the rows. I have to apply all these gradients, and these gradients are what the banging is that you hear. So in conventional diagnostic MR, you spend a lot of time hearing the banging because I'm moving across these rows. I have to strike a balance between the contrast between the tissues. I have to look at image resolution, image quality, how much time I'm spending. And that's why the scan takes a few minutes, because for a diagnostic application, the radiologist wants you to be in that scanner one time. And then they're going to do another acquisition that has a little bit different contrast between the tissues. But then, once you're done, once you leave the room, the radiologist maybe reads the images in a couple hours later, maybe the next day. And then they'll dictate a report. And that report will go to your referring physician. And the referring physician maybe will call you in a couple days. And later on, you'll sort of get the results. Now, one of the things our group recognized is we don't have to always move just in rows across the images. We could apply any kind of gradient set and collect the data, for example, in a spiral roll, and come up with a completely different set of trade-offs between resolution and scan time. So this is what a spiral scan would look like. I can set it up to do radial. That is, move in diagonal lines, and again, strike a different balance. And in fact, our group showed, hope this plays. Shoot. I don't know how to play this. Let me see. Hey,
If you press next, sometimes it plays.
what?
If you press next, sometimes it plays.
Oh, okay. Nope. I really wanted this to play. I'm just going to duplicate it because I really don't need it. Okay. No, it's not playing anyhow. Okay. So I've had this quote on my desk for years. Even before I came to Miami, before I was a dean, before I was a department chair, it's basically talking about make really big plans. Think about solving big, hairy problems. Because even if you move the needle a little bit, at least you've moved the needle a little bit on a big vision. You've gone somewhere new. But if you're always thinking small and you move the needle, who cares? So think big and try to move the needle. Oops. So what we said is, instead of using MR in this diagnostic arena, let's try to use it for image-guided procedures. Now, the image I tried to show you here was a radial scan that acquired images not in minutes, but in about 50 milliseconds. So we could get about 20 frames a second, which is pretty close to real time. And what this would have shown was a heart, and I'll show you afterwards, a heart beating with no synchronization at all. Okay? So we knew we could get something in the neighborhood of 20 frames a second with some of these different trajectories. And so we thought about, could we create a real-time system where each image was acquired in about 30 milliseconds, using to sort of create an MRTV, if you will, that would allow the radiologist to have an alternative to X-ray fluoroscopy and treat arterial stenosis. That is, deploy a stent completely under MR guidance, no radiation, and all of the advantages of MR. That is fantastic soft tissue contrast, no radiation, et cetera, et cetera. So We had developed some techniques where we could do image-guided biopsies. So this was virtually in real time. This was about 15 frames a second, where we could insert a biopsy needle into a tumor location. We could insert an electrode that would heat up the cancer, again, under MR guidance. We could watch the tissue heating up, and we actually could come up with models that would say what fraction of the tissue in that region was actually killed. So we did all of this before we went to this next step. And when I think of scientific research teams, you know, this is sort of the era that most of us grew up in, was sort of the independent single investigator. But the integrated research team is where everybody brings sort of a different perspective to the problem. And I think that this is one of the things that we were looking at. But it's also why, when I came here and, you know, was capitalizing on some of the work that the faculty had done here, is this is what the U-Link proposals are all about. This is about putting interdisciplinary teams of scientists together to solve really big problems. Recognizing that the first step is getting through that language barrier, the team barrier, things like that. But this is really why, from a faculty level, it was important for us to create the U-Link Awards. So why did we have this sort of crazy, audacious goal to go from a diagnostic setting of MRI to an interventional one, instead of going from minutes or tens of minutes to get a set of images that the radiologist would use to 20 milliseconds or less per image? When we looked at the competing modalities, and you looked at plaque, for example, using X-ray CT, you could see the impingement onto the lumen of a vessel, but you really couldn't tell anything about the actual plaque itself. So, as all of you know, atherosclerosis is a disease of the wall. It impinges on the lumen, but the disease happens here. And when we looked at other technologies like intravascular ultrasound, you could see some contrast between the tissues, but not particularly well. But when you went to MR, I mean, you could see pretty much everything. And so our goal was to couple all of these advantages with MR and really get rid of the fact that X-ray fluoroscopy was a projector modality, single contrast mechanism, X-ray or electron density, or X-ray opacity, if you will. We didn't want to image the vessel lumen. We wanted to image the disease in the wall, and we didn't want to give ionizing radiation. So this was our crazy goal. Could you make MR fluoroscopy replace X-ray fluoroscopy? So we talked to our physician colleagues, and they gave us, in our dialogue, a list of expectations. The real-time images had to be able to follow the catheter tip. The angiogram roadmap that we would acquire had to give the current position of the catheter tip in real time. It had to go seamlessly between when we were guiding the catheter to actually closely looking at the location, and a bunch of other things. And we came up with this sort of catchphrase that was, all of this technical sophistication that was really fun for us as scientists and engineers had to be hidden behind user friendliness for our physician colleagues. They didn't care about any of that stuff. Like, we thought it was great, we loved talking about it, but they didn't care at all, okay? So that had to sort of be our underlying premise. Group interactions create knowledge. You know, I don't think we would have had nearly the same perspectives if we hadn't recognized that different individuals really contributed differently and were the basis of our creativity. And we also recognized that there were some shared mental models that were important. That is, we had to agree on a lot of different things that were compromises between the technical and the physician need. What I wanted to do scientifically was not what my physician colleagues needed to do the procedures. It was particularly important because we each had different perspectives, and we each sort of had to recognize what everyone's role on the team was. Now, I'll share with you one interesting aside. I recruited to my research group a Japanese radiologist. He wanted to get his PhD. He already had his MD. And I put him on this project as a physician because I thought it would be perfect, because my physician colleagues at Case Western were so busy with their clinical obligations that I was going to have this full-time graduate student who was a fully trained radiologist from Japan on my team. And he was worthless because he didn't want to be a physician. He wanted to attack the most challenging mathematical problem in this space. He's probably the most productive graduate student I've ever had when I got my understanding of his interests and needs instead of my own for him. I wanted him to be a physician. When I finally realized he wanted to be a mathematician, our group was fantastic, and he contributed in amazing ways. The other thing I would say is it's really important for psychological safety in teams. That is, everyone has to feel comfortable in expressing their opinions. Everyone has to be able to express their ideas and their opinions, that they're welcome, and that you have to, everyone sort of have to model that behavior. And 3 words that can like kill team dynamics are but, however, yet, and no. Okay? So if my physician colleagues would say, can we do this? If I said no, the conversation would stop. But if I said, what about this? You know, or I don't know, what do you think of this? But no is much worse than why or why not or and. So avoid some of those sort of keywords. So we had to make a bunch of crazy things. At the time, there were no MR compatible catheters. So these catheters had to not only be able to be placed into an MR scanner, but it actually had to be able to detect the signal. So we needed some electrical engineers to work on that. And I actually brought one of our last devices here if anyone wants to take a look at it. So all of these are MR compatible receivers. This is our first prototype. They're sort of crazy and gross looking, but these are actually pretty nice. We had to completely modify a conventional, clinically FDA-approved scanner to acquire new types of acquisitions, to display the devices, to update the image resolution and slice position, to update a bunch of information in front of the physician, and do all kinds of other stuff. And we said, yes, we can do that, and we did it. And this was what the user interface looked like. All of this stuff that normally would have been the parameters that the radiologist would have changed for their diagnostic scan, completely automated and adjusted on their own. We had to go through and come up with what was the experimental protocol that we would use to validate whether this was actually working like we thought. And because we were comparing to sort of conventional imaging, we came up with ways to acquire X-ray angiograms and do the parts of the procedure under a normal type of acquisition, but then compare it to what we got in MR. And so all of this then is sort of what the MR images look like. You can see here the renal artery stenosis. This is an MR scan. You can sort of see it here too. This is a physician doing the procedure. This is a pig model. We could confirm the size of the stenosis. And we could look at how well that compared to actually what you got with an X-ray angiogram. And in this particular case, the difference was less than about 0.5%. Fantastic results. So let's see if this works. Oh, it did. So that's good. So this is the catheter being inserted. And you can see the image resolution changing. And in a second, you'll see the slice position change because it's following the catheter. It just changed there. And we're going to go up into the renal artery. If I can start this one. Okay. What you'll ultimately see is the catheter engage the renal artery, go across the stenosis. You can see it going across there. You can see the tip of the catheter going in the collecting system of the kidney. And if we were to watch this long enough, you'd actually see the stent being deployed.
Something happened to that kidney on the left, it was all lacerated and swollen, the left kidney.
I'm sure it is. I mean, this is a pig model, so it's been stenotic for probably 2 weeks at this point, 3 weeks. So we were able to look at and confirm the preoperative stenosis with our MR acquisitions. We could compare that to the X-ray imaging, both pre and post treatment of the stenosis. And ultimately, I think what we were able to show, and so ultimately with a bunch of other work, ultimately not only for the image-guided sort of cancer procedures, but in this particular case on the cardiovascular stuff, I really think we and others, it wasn't just our group, there was others working in the space at the same time, really started the transformation of MRI from a diagnostic to an interventional tool. Our performance was as good or better than conventional X-ray, both in terms of accuracy and time. But most importantly, I think we created an effective team with mutual respect, and from my perspective, it's probably the most fun I've had in my research career. Now, this job is great as a provost, but as a research scientist, this was really one of the great things. And there's been a lot of research done on what makes teams smart, what makes it so that, you know, if I look back, what would be some of the lessons learned that the actual scientific literature, you know, supports. Basically, teams that have general intelligence, that is, teams that have done well on one task, tend to do well on the next task and the task after that. So it happened that we were very successful in getting MRI to be used for diagnostic procedures like taking a biopsy or treating cancer with thermal therapy, for example. And that sort of gave us the confidence that we as a team would work together and we could sort of attack bigger problems. Now, we didn't know this, but I think in retrospect we would agree with this. It's the smarter teams, as the literature says, the smarter teams are not those with the higher IQs, the higher average IQs. It's something more than that. And it's not that it's necessarily the most extroverted people or those who are reporting more motivation to contribute. There's other factors beyond smartness and extrovertedness and other factors of motivation. It really is about how the team functions as opposed to who the members of the teams are. Smarter teams in general have equal contributions from the members. They score higher on measures of reading, emotional intelligence. Be able to say, are you having problems today? Or I get the feeling that you disagree with my approach to this. So being able to read the audience, being able to read the other members. And also the literature supports that better teams, more smart teams, typically have more women. So for the women in the audience, I think you knew that already. I suspect you knew that already. But I think really effective teams need to agree on the goals. They need to have shared mental models. That is, what are we really working on here? What's our ultimate goal? Need to acknowledge and manage conflicts, as I said before, that ability to sort of read each other, that whole idea of emotional intelligence. And you need people who are going to step up at different times and take the leadership role and be able to call others out and say, hey, either you're not carrying your weight or alternatively, I'm going to get your back here in a little bit. I know my role is coming up here down the road. So that's knowing both when to be the leader and when not to be the leader. And like Nike says, just do it. So in theory, you know, there is no difference between theory and practice. In practice, there is. This is the famous quote by Yogi Berra. So thank you all very much for your time. And yeah,
so,
Eddie.
Thank you for the very, very interesting presentation. Now, are you still keeping up your contacts with this and developing a catheter that will be approved for human use?
No, in fact, the company that was started that is with this went out of business a couple years ago. But there are others who are doing it, not us, not my team anymore. Yeah.
So the department has started an industry seminar series to help, right here, to help educate our students from leaders in the field who've done the translational journey. So you touched on the early parts of it, talking to physician collaborators. But could you touch on how did you take this research ideas to the product that's being passed?
Yeah, that's a great question. So even a lot of the technologies I showed here ultimately got incorporated into Siemens' product. So we had for my entire time at Case, we had a sponsored research agreement with Siemens where they would, it started off where we sort of proposed this crazy idea of image-guided MRI for catheter, or for biopsies and some other stuff. They liked the idea. And then once we sort of demonstrated on it, then we started telling them what we wanted to work on. So for the entire time I was at Case, we had a very close working relationship where we were developing works-in-progress packages and pre-production prototypes for Siemens.
Purely as sponsored research, or were they licensing your patent?
Both. Both.
Short of having a partner lined up, how would you go on?
Yeah, so the catheter was a really interesting story. We were at the big MR meeting, and a company came up to us that we knew, and they said, we would like to sponsor your research, and we would like to, try to remember what the deal was. I think, if I'm not mistaken, they were willing to give us something like $300,000 a year for 3 years to develop a prototype that was FDA, that would be FDA approved and could be used in humans. And we turned that down. And the reason we turned that down is we had no capacity to make FDA approved devices. So it turned out that there was another company there who came to us and said, we would like you to do a startup, and we would like to own 19.9% of the startup. And they were willing to give us $1 million for that. And we knew then that our company was worth about $5 million before we'd done anything. And we asked them, you know, why 19.9%? And they said, because if it's 20%, we have to show it on our balance sheet. But if it's 19.9%, it's an investment, or it's a, you know, it's a different structure. So we got that. But again, we sort of couldn't commit to the timeline, so we had to turn that down too. And in Ohio at the time, they had money for basically commercialization. And so we had these two groups that came to us, and so we got state money, formed our own company, and that way we could define the timeline. So, and we raised a couple $1 million, we went out of business. So, you know, it's, you know, people knew the risks, but that was also a really fun time of the year, or of my career, to sort of be trying to define what the future of MR devices were going to look like, besides just what MR technology was going to look like. So, yeah.
What do you see as your role as provost to provide a culture where this can happen?
I think it's really a couple different ways. One is like with these U-Link awards, which are these interdisciplinary team science awards, to look at, you know, sort of what are the topics that faculty are really interested in pursuing from an interdisciplinary perspective, and then providing, in some ways, the first amount of money to get that collaboration going. And if any of you looked at sort of the U-Link proposals, the first milestone was typically pretty small. It was like run an experiment, write an outline of a paper, you know, write the aims page of a grant, you know. I mean, but then to get to the second phase, you know, awards which were bigger to actually get the data and do the work. I think that's an example of the kind of things that we can do. The other one I would say is certainly one of the things we're very focused on now is really getting, and I think this is to your point, Ashu, is getting more companies onto campus. I spent the last 2 days, I was at Canon a couple days ago, and where was I? I forget where else I was this week, but there were 2 companies I visited with this week just to that purpose, was trying to create new kinds of relationships for us on campus. Yeah. Yeah.
I know you can realize I'm not a student.
That's all right.
I'm a radiologist at the University of Miami.
Uh-huh.
And I would like to hear your thoughts, Idris, this is the first name Madras, your thoughts of the future research opportunities in MRI.
Yeah, so I didn't talk, I mean, there's a lot of really interesting things. So the intersection, there's 2 ways I think MR is going to change, 3 ways really dramatically. One is the amount of information we need to collect, I think, will get much, much less. So right now the scan times, you know, even your probably standard clinical protocols for T1 heads, maybe a couple minutes, you know, 1.5 minutes, 2 minutes. I think that will go down into the seconds or fraction of seconds as some of these new reduced data sampling schemes come available. So speed will change, I think, by an order of magnitude again. Now, we're about the same age. When I started in the field in 1983, the typical slot for a patient to come into a radiology department and have their clinical scans was about an hour, 45 minutes to an hour on the scanner. hasn't changed at all.
It's still pretty.
Still 45 minutes to an hour. Now, in those days, we maybe would get 60 images, and now we probably get 3,000 or something. I mean, it's just the amount of information that the radiologist has access to is dramatically different. Second one is machine learning. I hate to say it, but you guys are going to be out of a job in 20 years. Because anything that has to do with pattern recognition or visual interpretation, machines are going to win. So you're fortunate that, you know, but I think that's going to be a big change. And then the third is going to be the intersection of contrast agents and biology. You know, so think about how long gadolinium has been around. It hasn't, we are still at the infancy of contrast agents, and this is where PET has probably done much better. FDG is easy to make. It, you know, it has a long half-life. If you have your own cyclotron or your own generator, the number of contrast agents you can create with PET is far superior to MR, and it's quantitative. So those are three things I think that'll be very different for MR.
PET MR is going to be.
PET MR is interesting, but that just makes PET the contrast agent for MR. So I don't know. I mean, if I had one to play with, I would love it. But, you know, yeah, Eddie?
So one of the reasons why we haven't been able to cut the imaging time down is because an MRI, if you want a sagittal coronal transverse, you got to image each one specifically for that. In the high resolution spiral CT now, we can just do a volumetric acquisition in 5 seconds and make any reconstruction we want in any plane. So do you foresee a development where perhaps we can acquire a volumetric data set and then make the acquisition in image sequencing afterwards?
Yeah, there are. My former group at Case, we had real-time 3D cine cardiac scans. So full isotropic 3D scans of the heart in real time. So yes, that will easily be here very quickly. Yeah.
So you talked about you kind of bridge these gaps, but you know, 14 years ago you published this paper with the cardiology group. Could you do that same work here, based on what you know about the infrastructure and the medical campuses that are, you know, the cardiology group may be? What do you think you're actually getting that work done here?
Well, like I said, you have to be patient. So those images that were acquired in 2000, 2005, I had already been there for, I don't know, 19 years at that point, working on my startup package was $3,500. I bought a computer with it, and then I wore my fingertips out writing grants. Yeah, it can be done. I mean, you have to build for that. I mean, my first thing was write a paper. And once I wrote a paper, I wrote another paper, and then I could be competitive for grants. And then I got a grant, then I got a graduate student. And, it takes time, and the big vision, you could not have done any of this work in 1983 because the technology hadn't evolved to that point. The gradients weren't fast enough, the RF coils, there was only one coil typically for each body part. So none of us would have ever imagined in 83 or 84 that we would be doing real-time image-guided procedures in 2005, 2010, and then we had to create our own courses to teach MR physics. We wrote our own book. We had to, so that's what I meant earlier about being patient. You just sort of have to, but we were always attacking important problems in the field so that we could get grant funding and things like that. And where the grant funding and our own scientific curiosity led us 20 years later was this crazy idea of doing it. But that wasn't our idea from the beginning. I mean, that would be complete BS if I said that. Well, thanks everybody. It was really fun for me to talk about MR.
Before you leave, I'd like to give a little token of appreciation to Jeff. It's a little device here we use commonly on the beach.
Oh, wow.
And we're trying to induce our provost to visit these particular areas next to the coastline. So, Jeff,
Thank you, JP. Thank you.
hope you enjoy it.
I think you can tell I've been there a little bit. Thank you.